Hello YouTube, and welcome to 2016, let's see, AB1. Let's take a look at AB1. BC1, right? There it is. Now we've done this a number of times already on the 84, on the TI Inspire, and on Sage. I'm just going to show you the details on the TI92, okay? So, water is pumped into a tank at a rate modeled by W of T liters per hour from 0 to 8 inclusive, where T is measured in hours. Water is removed from the tank at a rate modeled by R of T, liters per hour, where, whoops, what happened there? Where R is differentiable and decreasing from 0 to 8 inclusive. Selected values of R of T are shown in the table above. At time T equals 0, there are 50,000 liters of water in the tank. Estimate R prime of 2, show the work that leads to your answer, indicate units of measure. So let's use the mean value theorem that says that the slope of the secant line from the point 3, 950 to 1, 1190 should match the slope of the tangent line somewhere between 1 and 2, so namely T equals 1 and 3, namely T equals 2. Alright, so we're just going to do the slope of the secant line. So let's see. Let's open up a TI92, which is a lot like the 89, by the way. And let's see, open parentheses for the numerator, 950 minus 1190. You really don't need a calculator for this. You could do this in your head, but just to show off the calculator, divided by the quantity 3 minus 1. And you get negative 120. Now, they also want you to state the units of measure. Well, the numerator is delta R, and the denominator is delta T. Delta R is in liters per hour, and delta T is in hours, so negative 120 liters per hour, or if you must, liters per hour squared. Okay, now what? Let's see what happened here. Now, part B. Use a left 3-month sum with 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. Is this an over or under estimate of the total water removed? Give a reason for your answer. Well, if you graph these values, notice it's a decreasing differentiable function, right? 1340, 1190, right? So if you do what do they want now? A left 3-month sum, that's going to be an overestimate, isn't it? So what is it going to be? Well, look at the first 2 entries in the table. If delta T is 1, the base of the Riemann rectangle is 1, the height is 1340. Alright, then between 1 and 3, for x T equals 1 to T equals 3, delta T is 2, and the height of the left Riemann rectangle is 1190. And then from 3 to 6, delta T is 3, and the height is 950. And from 6 to 8, delta T, the base of the Riemann rectangle is 2, and the height is R of 6 is 740. Alright, so just put that in the calculator. Alrighty, so let's see. Let's clear all this stuff. Okay, now let's write. Alright, so let's write what we said. The first delta T was 1, times the first left Riemann height was 1340, plus the next delta T was 2, times the next height was 1190. 1190. Whoa. Okay. Plus the next delta T was 3, times the next height was 950, and the next delta T was 2, times the next height is 740. And so you get 8,050. Now what are the units? Well, the delta T's are in hours, and the delta R's, well, the heights are in liters per hour, right? So liters per hour times hours is liters, so 8,050 liters. And you can write that down on your paper. Okay. You can show your work on your paper. You can even graph the rectangles if you want. Okay, question 1, part C, AB1, BC1, part C, says, use the answer in part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Okay, so we lost 8,050 liters in 8 hours. At least that's our overestimate with the left sum. We started off with 50,000 liters, but we're gaining Well, WT is in liters per hour. If we integrate WT from 0 to 8, we're going to get the total amount of water pumped in. right? Okay, so let's write that up into the calculator, just showing off the TI92 for those purists who've missed the 89. I don't have an 89 emulator on here, but close enough. Okay, so here's your 92 or TI200, TI Voyage, precursor to the Inspire, of course. All right, so you got 50,000 to start, and in part B we lost 8,050 liters, but now we're going to add on the integral from 0 to 8 of W of t, right? Okay, so let's see how we're going to do that. Let's see, how about a second math, calculus, and integrate is number 2. Whoops, number 2. Okay, we're integrating the, I think it was W of t is 2,000. Just type it in. E to the negative t squared over 20. Okay, so e to the is second ln. Negative is the gray key. Now, alright, I could use t here, I suppose. Let's see, t squared. Where's my square key? I forgot how to use this keyboard. Is there an actual square key, or is it just a caret? It's just a caret. Okay, caret 2. Divided by 20. Order of operations, it'll square before dividing. That's the exponent. That's your quantity with respect to t from 0 to 8. Alright, so we don't have the pretty print here. And you end up with, and they want this to the nearest liter, end up with 49,786. There you go. To the nearest liter. So you write that out. 5,000 plus, 5,000 minus 8,050 plus the integral from 0 to 8 of WT dt is approximately 49,786 liters. Okay, good. Next part of the question. Hang on, where is, don't I have this file? Here it is. Why isn't it loading? Okay. And part D. For t equals 0 to 8, is there a time t when the rate at which the water is pumped into the tank is the same as the rate at which the water is removed from the tank? Explain why or why not. Well, in other words, we want W of t to equal R of t. Alright, when is W of t equal to R of t? Well, doesn't that mean W of t minus R of t is 0 somewhere? Alright, so since both W and R are decreasing and differentiable, the maximum value is at t equals 0 for W minus R, and the minimum value would be at 8. Well, what is the maximum value at 0 for the function W of t minus R of t? Well, R of t is 1340. R of 0 is 1340. What's W of 0? Aha, let's find out. Let's go to the calculator. Alright, I probably should have graphed this crazy thing. But it's 2,000. Let's type this again. It's 2,000. You know what, how about if we just put this into a y equals, diamond y equals, like we're going to graph it, alright? So it's 2,000. Now we're in function mode, I presume, and so we're going to have to use x here instead of t. So e to the negative, let's see, e to the negative x squared over 20. Okay, there you go. And I don't actually want to graph it. I'm just going to use it. So go back to the home, and let's find, it was y1 of x for y1 of 0, right? So y1, like I think here you can actually just type y1 of 0. It's been a while since I used an 89. Here we go. And exactly, it is 2,000, right? Because look at it, if you plug in 0 for t into 2,000 e to the negative t squared over 20, right, that's got to be it. Alright, so the maximum value is 2,000. That 2,000 minus the R max, R of 0 was 1,340. So the maximum value of W minus R is 660. Now what's the minimum value? Well, let's find, let's see, on the table, what R of 8 is. R of 8 is 700. But what's W of 8? Well, W of 8 would be y1 of 8, right? So, how about if we type y1 of 8 for your W of 8 minus 700 for your R of 8, and you get, well, I want a decimal for this, a diamond enter. Negative 618. Okay, so the maximum value of W minus R is 660. The minimum value of W minus R is negative 618.476. So you could say that by the intermediate value theorem, there must be a value somewhere in between, such that W minus R is 0. In other words, W of t equals R of t. Let's just write a little sentence about that, quoting the value of W of 0 minus R of 0 and W of 8 minus R of 8. W of 0 minus R of 0 is 660 and liters per hour, and W of 8 minus R of 8 is negative 618.476 liters per hour. And that's it. Okay, that's it for today. Thank you. I hope that was helpful. Bye-bye.